Testing, testing. Welcome to, this is CS3510. I forgot the number. What's the number for today? 16? That's not possible. Should either be 14? 14. L14A, Maxwell min-cut theorem. This is one of those things that I think is like really important, but more the fact that it is important, it's very surprising. So the Maxwell min-cut theorem basically says these two things that are very different are actually the same. That's kind of the surprise. And that'll be a common theme as we get into next lecture with what's called duality. Two opposite things end up being equal to each other. So solving for one means you can flip-flop between both problems to find the actual solution. Something like this. What is the max flow problem? You're given a flow network. A flow network is a graph with specified vertices S and T. Then there are other edges directed that have what are called capacities on them. So let's get 2, 7, 1, I don't know, 4, 3, something like this. Let's just make up numbers. Each edge has a capacity called CUV, right, for vertex UV. And we specify that we may send a flow over it of f of UV, which is not negative, right? So every edge has what's called a capacity. And the capacity allows you to send over it a certain amount of flow. And flow could be, for example, a number of trucks per hour. It could be the width of the road, you know. And flow networks are very important as a kind of a basis optimization problem because everything looks like kind of a flow network in some sense. The problem is, what is the maximum amount of whatever it is you can send from S to T? That is the problem you're trying to solve given a specific flow network. There's other constraints that must be that exist. For example, the sum of outgoing edges of any vertice must equal the sum of incoming. So for example, if you have some vertex like this, and let's say you have 2 and then 3, it must be the case that what comes out of there must be the same. So like 4, 1, right? The sum of the incoming must equal the sum of the outgoing for each vertex. You cannot send trucks and then have them park themselves somewhere, okay? Notationally, we will for an edge with capacity C, we'll say f/c to mean the capacity we want to send over that edge, right? Important in kind of these kind of problems is the fact that you can't necessarily send as much as possible because there are bottlenecks throughout the whole system, you know. And this is something traffic engineers, specifically in Georgia, don't really get. But you have like if you add like 10 lanes to a highway, it doesn't really matter if everyone has to get off at the same exit, right? So it doesn't matter how wide you make the road. In the case that everyone, the rate of cars or transportation or whatever is still bottlenecked by the slowest point. So it doesn't matter how wide a road is. Adding more lanes a lot of times doesn't really do anything because you still have to get off the highway. It may just increase the time it takes to get on and off the highway, for example, right? Similarly, let's say we want to send some units, let's say trucks from S to T through the above path. We cannot send two trucks through the above path, right? Why? Because there's a 1 there. So we could send 1 truck through the above path and 1 here. And we would know that 1 truck was able to reach T from S through the above path, right? Oh, the other constraint is that S has no incoming. T has no outcoming. Right? S is the start, T is the destination. That's okay though, even though you can't send more than 1 truck up here, you have a route here that can hold capacity 7. So what you do here is you can send 2 through here, and then you send that extra guy through here, right? Now you can send 3 trucks down here, and you have 3 incoming, 1 incoming, you can send 4 through here, right? So one of the trucks, unfortunately, has to take a long route. That's okay, though, because we're able to send a total of 5 trucks from S. They exit S and they enter T, right? This is the flow network. And it's not necessarily the case that, given a flow network, you can always what's called saturate the edges, which is like have them of maximal flow. For example, if this was, let's say 18, it doesn't really matter that at such a large capacity, you could never send more than a certain amount there, right? By the way, how many units are possible from leaving S? 5. You can't send anything more than 5 to S, right? But you can receive up to 19 to T. That doesn't matter. S can only send at most 5, right? So given a flow network, we're concerning ourselves with what's the max flow. What is the maximum amount of units I can send over such wires, whatever they're framed as, to begin at S and end at T, such that the capacities satisfy these flow constraints, flow is conserved, and S has no incoming, T has no outgoing, right? This is the definition of the max flow problem. Are there any questions on this? Have we seen max flow in some other scenario? Okay, maybe I give you a hard graph and you tell me what the max flow is. Let's just do it over here. Okay. Suppose I have the following flow network. Let S be the origin and T the destination. What is the maximum flow I could send from S to T? Or just give me some examples of flow. Find a path, fill it with some flow. Is it second? Second what? 7? Why is it 7? Not just a numerical number flow, but find the actual flow. Yeah?
I was going to give a number.
Yeah. Oh, okay. Well, where would you put those number of trucks?
I was going to say 12 because you can't send more than 12 from S given the 3 paths.
Correct. But notice, T can't receive more than 7. So the flow is upper bounded by 7 at least. What about, but give me an assignment of trucks. Just start labeling vertices.
S, C, E, T.
S, hold on, how many do I send from S to C?
4.
Okay, I'll send 4 there. And then how many do I send from C?
You can only send 4.
Okay. And then what about E?
Send up to 5 from there if you go an upper route too.
Okay, so let's leave this unspecified for now.
Yeah.
Okay, then what do I do?
I want to say S to B can send
S to B, okay.
1 or 2 only.
Okay, well tell me which one is it?
Send 1.
Okay.
And then B to D send 1.
Okay.
And then D to, wait, no, go back to S. S to A send 2.
Okay.
A to D send 2.
Okay.
And then D to T send 2. Wait.
Okay.
And then D to E send 1.
But we already sent 2 from A to D to T.
Right, but there's the 1 from B to D, right?
Oh, yes, I see. Yes, there we go. So 2 trucks go up in the above path. 1 truck goes S, B, D, E, T. So this 1 truck joins this convo of 4 at the end. And is this a conserved flow? This is going to be 5 then. So 2 and 5, okay. 7, 4. That looks right to me. So that's a flow of 7. Now, here's the thing with algorithms. A lot of times you solving problems is different than algorithms because you just look at it and you're like, okay, that's the answer. But an algorithm has to do it in general. And you have to be convinced that the output of the algorithm is correct. So, are you convinced that the output of your algorithm is correct?
It can be more than 7.
Okay. Can you do that in general? Yeah.
Well, couldn't you reverse all the edges and work backwards from the sink?
I think that would be as hard of a problem, though. That'd be just a different flow network. hold on to that idea as we do the actual algorithm, it turns out, because that's going to be important. But did you want to say?
No.
Okay. That'll end up being a core idea in the algorithm, it turns out. But if you just do the whole graph like that, you'll just get a different flow network, right? Notice that you're kind of bottlenecked by cuts. So what a cut is, a cut in a graph is just a cut of G is a partition L comma R is a set of edges such that it's the sum of the capacities for U in L and V in R, something like this, right? So it's the sum of the capacities of those cuts. We also want the fact that S must be in L and T must be in R. In some sense, you have a flow network. The cut of a flow network is defined to be some partition of the vertices into lefts and rights, and then you sum over the capacities. For example, this is a cut, right? And then you would sum those two outgoing edges. This is also a cut. And notice that we argued the capacity, the flow of a graph could not exceed outgoing of S or incoming to T, right? And in some sense, those are two specific cuts, right? But there are other cuts. Here's another cut. Here's another cut. And even independent of ways you could draw the graph nicely, there are cuts, right? It doesn't need to literally be a chop of the graph, but that's a cut. So the problem of finding a max flow is literally, in some sense, the maximum amount you can send. The minimum cut problem is the opposite problem. It's, in some sense, if you have, for example, a rail network or something, what is the fewest amount of bombs you could drop to totally disconnect a front line? Actually, both these problems are highly motivated by war. Right? You want to send as many trucks to the front line full of supplies as you can. That's a max flow problem. They have to go through certain checkpoints or whatever. The min cut problem is if you want to cut off at enemy supply lines, what's the fewest number of roads you need to break up to fully disconnect the thing. So we're concerned ourselves with the minimum cut problem. What's the fewest edges you can disconnect in some sense that will take S away from T? That's what the minimum cut problem is. So for this specific graph, we have two cuts right now, right? We have the cut which only contains T, which would be 2 plus 5. And the cut is defined as the sum, not of a flow, but of a capacity, right? So we have one cut right now of S and T, which is 2 plus 5 is 7. Do we have any other cuts that are smaller?
So you're saying if you cut dt and the et, it will disconnect S from T?
D, T, and ET, correct. That would disconnect S from T. Let that be the cut. And formally, the cut is a set of vertices. So the left part of the cut would be everything here. The right part of the cut would just be T, right? The edges that cross from L to R would just be DT and ET, which would be 2 plus 5 is 7, right? Can you find a smaller cut? Let's just find some other cuts. Yes?
You mean cuts in terms of capacity?
Yes, with some of the capacities, but not the flow. Yeah. Here's another one. Let's just do this chop, okay? That's 2 plus 1 plus 4, which is what? That's also 7. Okay. What about this cut?
Can you cut and skip or not?
The cut is not defined as the picture of the graph. The cut is defined as the edges that are in fact outgoing, and the incoming edges you just ignore. They're 0, right? So you can draw the graph any way you want and then call that a cut. But it may be difficult to do that in practice. But just, by the way, today's thing, we'll talk about an algorithm. We won't even talk about the runtime because it's going to be like kind of conceptual. So in that spirit, it's the same thing. It's like think of a cut literally as chopping the picture. Know that formally that's not what's going on though. What's the capacity? What's the value of that cut? Yeah, so that's 8. What other cut? Just give me any other cut.
C, E, D, E.
Sorry, hold on. What?
Like that.
Like this.
Nope.
Like
That.
more of a straight diagonal through through the 2, the 1, and the 5.
Like that. No, like this. Just tell me where to start. Here?
Sure.
Okay, and then go down
Yeah, just diagonal.
to here. Oh, okay.
The other diagonal too, like the,
Oh, so like this.
yeah, sure.
Okay. So what is that? The outgoing edges here are 2, 1, skip, 5. So that's 2 plus 1 plus 5 is 8, right? Okay. So why do we care about this? What is the relationship between a maximum flow problem and a minimum cut problem? It turns out that the maximum flow is always bottlenecked by cuts. If you think about it, if S is over here somewhere, and T is over here somewhere, you have a certain number of bridges from one half to the other. The sum of those bridges is the max you can send. That's sort of a little bit of a generalization of the fact that where we said the max flow is upper bounded by the max of S and the max that S can send or the the max that S can send or the max that T could receive, right? It's true not just for those cuts at the extremal level, but any cut, anywhere you can make a random diagonal that you can think about the bridges bottlenecking transportation from one to the other, right? It could be the case that there's a single edge that would bottleneck the whole flow network. That might be possible. It'd be kind of weird and unreasonable, but that would be an example. Now, what is the max flow min cut theorem? If anyone had to guess. Yeah, the maximum flow in a graph is equal to the minimum cut. We'll prove that kind of in discussion with the. So if you have a set of, we found a few different flows. What were the flows that we found? We found one of 7, right? But we found some other ones, didn't we? We found one of 6, without sending this B path. We also found one of just 2, and I think we found one of 4, right? So those are your flows, right? But what are your cuts? Your cuts, we found one of 7. We found one of 8. We found another one of 8. We didn't try too hard, but we could probably find bigger ones, right? What the max flow min cut theorem says is whatever your smallest cut is equal to whatever your largest flow is. These two values are equal. That's the max flow min cut theorem. Let's describe an algorithm that finds the max flow in a graph, and it will use the fact that there exists a minimum cut in the graph as sort of a correctness of the algorithm. Okay. If you have an algorithm, here's another important detail. A lot of times algorithms don't output an answer that can be easily certified. For example, if you output, let's say you're looking for the minimum spanning tree. In the context of like NP, how can you quickly convince someone that you found a minimum spanning tree? It's polynomial time, so this is not perhaps the best example. But it's hard to convince someone quickly that there is a minimum spanning tree without them just kind of like recomputing it for you. But in some sense, the max flow can be certified because you give them a flow and you say, I can prove to you that this flow is optimal. It's the best flow you can expect. Why? Here's a matching cut. So if you have a cut, the cut in some sense is a certification of a flow. You can convince someone that the flow is optimal by outputting a cut of the same value, if you believe the max flow min cut theorem. Do we agree with that? Do we understand that part? The cut can be used as a certification of an answer. The fact that the cut is equal to it means that there is no flow that is greater, right? So you can be convinced that they didn't forget a truck somewhere or something, right? Yes?
Why wouldn't you have to verify that it's also the min cut? Like, is it necessarily?
And we'll elucidate that. But notice the way I've arranged those two sets. If any, it'll turn out to be the case, and that's a great question. It'll turn out to be the case just from basic math stuff rather than algorithm-specific stuff. But if any flow equals any cut, it must be a max and it must be the min, right? Think about if you had a smaller cut and a larger flow, that would violate something, right? That's a great question. We'll have to come back and answer the max flow min cut after we talk about the algorithm in specifics. The reason I want to talk about the algorithm is because it uses the max flow min cut theorem as kind of its stopping condition. And that's kind of where the correctness follows. The algorithm is not really an algorithm in the sense that we have like very precise definitions of code. And many people can take the algorithms that we've talked about here and actually implement it. So the algorithm, quote unquote, we're talking about is Ford-Fulkerson. Ford-Fulkerson is not a real algorithm in the sense that you could go and implement it. It's really just a high-level description of the maximum min-cut theorem, which they proved. If you start making more algorithmic decisions about the Ford-Fulkerson, it's called different things. You start using BFS-defined paths, now it's called Edmonds-Karp, and so on. There's all kinds of little changes. And there's a rich amount of science being done engineering-wise on max flow algorithms. But they all kind of follow from the correctness of the max flow min-cut theorem. So this is an algorithm. We won't even really discuss its runtime or anything like this, but we'll kind of discuss its correctness because that follows from the max flow min-cut theorem. And then perhaps you could believe lots of little engineering details could be made to improve it, right? Hold on, my camera is blurry. Hold on. Hold on. Hold on, sorry. Please, please. Sorry, hold on. There we go. Sorry. It's crazy. All right. Okay. The Ford-Fulkerson algorithm proceeds as follows. It's basically a greedy algorithm. Let me try just doing this here. It's basically a greedy algorithm where it just repeatedly finds the maximum flow it can send on individual paths. But the problem is that a greedy algorithm doesn't really work for this problem. You could be convinced yourself that sending too many trucks down one path may prevent you from sending a sneaking amount of other trucks from some other path, something like this. So what Ford-Fulkerson basically is a greedy algorithm, but it modifies the graph, a copy of the graph called a residual graph, in such a way that future greedy decisions can undo past greedy mistakes. And that is basically what all Ford-Fulkerson does. We keep a residual graph called GF. And when we take, when the graph G is assigned, let's say, a flow of the following, F comma C, we are admitting that we have some capacity C, and we're sending F forward, right? So what we can do in the residual is agree to send that F forward. We could undo that sending F forward by sending F backwards, right? Here, if we choose to send F forwards, that decision can be undone by sending F backwards. So what we do is we agree to send the F backwards, and we can also send, let's say we have a capacity C and a flow F, right? We've sent F so far. We could send up to C. How many more things could we send? So this is all the residual graph does. Every time you choose a temporary amount of flow to send, you modify the residual graph in such a way such that you update this capacity to be C minus F, because that's how many you have remaining. And then if you want to undo a decision, you update this backwards edge to be F. So in some sense, a path could choose to say, oh, I want to undo some of that because I want to send something else from somewhere else. It could do so by finding a path backwards that way, in some sense. This will become much clearer as we actually do the example. But this is sort of the idea behind the residual graph. And that's really all Ford-Fulkerson is. So here's the actual code. All right, here. We want to initialize the residual graph as G. So it's going to begin as a copy, a direct copy. While G, the residual graph has an ST path, we're going to find a path, compute its bottleneck, we're going to augment the residual graph as follows, right? And then flow is going to plus equals this bottleneck. Right? So what's going to happen is we're repeatedly going to find paths. We're going to compute the bottleneck of a path. And the bottleneck of a path is simply the minimum of the edges on that path. Okay? Then the bottleneck is then the max you can send along a specific path. Right? You update the flow by increasing it to the bottleneck, B. Then you make sure you modify the residual graph in such a way that it keeps track of these things. Right? This is not an algorithm in the sense that you could go off right now and implement this. There's a lot of decisions that need to be made. For example, how do you find paths? Just name any way to find an SD path. Dijkstra's, that would work, but it need not even be a shortest path. Answer? That would work. That sounds slow, though. But we're not concerned ourselves with runtime. BFS, just BFS for an SD path, right, in the residual graph. Notice that we're finding a path in the residual graph, right? And we repeatedly do this until we have no more paths, right? Let's go through the example execution very slowly, and that'll elucidate how the maximal min-cut theorem works and also why the algorithm is correct. But basically, as we repeatedly saturate edges, the graph is going to become more and more disconnected, right? So intuitively, if we repeatedly had 7 like this, right, and then let's say 2, if we saturate those edges, after some decisions, we're going to have edges that look like this, right? So eventually, the edges are basically going to flip. And what that's going to mean is that S is going to be disconnected from T eventually, right? And it's going to do so when we found the max flow. So when it's disconnected is when we'll find our answer. That's sort of the idea. Let's just do the example real quick. Any questions high level before we go through the example? Again, Ford Fulkerson does not specify how you find the path. It doesn't specify anything. And if you make decisions like that, then it's called something else. Again, if you find paths with BFS, then it's called Edmonds-Karp. There's Dinix. There's all kinds of slight versions. It's like Kruskal's versus Prim's. It doesn't really matter. And they're really dependent upon the way Kruskal's was dependent upon the cut property. Basically, every max flow algorithm is dependent upon the max flow min-cut theorem in some sense. So it's really more important you understand that part rather than specific implementations. You can leave that job to engineers. Let me give you the graph real quick. It's the same one. Who would have thought? Okay. Let me just double check. Yeah, that's probably right. Okay, now suppose I gave you the order we found the paths in. Okay. Let's find the paths over and over. Let's compute the bottlenecks and augment the graph, okay? So let the first path be S, A, D, E, T, right? So we go S to A to D to E to T. What is the bottleneck of that path? 1. So we are going to assign a flow of 1 and insert backwards edges of 1, right? So this is going to be 1. Well, let's just do this. This 3 becomes what? 2, and we send a backwards edge of 1. This 2 becomes a 1, and we send a backwards edge of 1. This e to d becomes a 0, and we send a backwards edge of 1. Edge of capacity 0 is basically not an edge, right? So we could have in some sense erased it and just say we flip the orientation. And sometimes max flow is taught as like negative capacity is just orientation is opposite. But it's fine. And then we go ET. So this 5 becomes a 4, and this we can go T to E with 1, right? I think I already made a mistake. It's supposed to be SADCET. SAD, yes, not E. SADET, no, sorry. So we go SAD, and we go C, this is going to be a 0, and we're going to go back to with a 1. And then we go C to E is going to be 4, we're going to make this a 1. And then E to T is going to be 4, this is going to be 1. Okay, there we go. That's right now, right? All right. Make sure I don't make any mistakes like this. SADET. Now notice though that we're finding paths and we're doing exploration not on the original graph, but on the residual graph. So what that allows us to do is as we insert backwards edges, we find paths that allows us to undo quote unquote mistakes that we may have made through greedy selection. So let's suppose we go SADET, right? What is the capacity? We go S to A to D to E to T. What is the max, what is the bottleneck on that graph? It's supposed to be 1 as well, right? It's 1, right? So we're going to update each of these to be 1. So this is going to become 1, and this now becomes 2, right? We go A to D with this edge of weight 1, which is now 0, and then this becomes 2, right? So notice that we went from 2 forwards to 2 backwards. Basically what that means is this edge is fully saturated. So now, after we finish this path, there's no longer a path from A to D. It's gone. Any other path we find has to go some other route, right? Or maybe undo that. We go D to E by going this 1 to 0, and we go backwards. 1. And then E to T, 4 becomes 3, 1 becomes 2, right? Question?
So you decrement the forwards path by B, and then you increment the backwards path by B?
Exactly. Why? Because you've sent forward. The forward edge should keep track of how many more can you send. The backward edge is how much have you sent in case you wanted to undo it, right? So for example, here, we originally started with a forward capacity of 3, right? But now we've technically sent 2, right? So now we can send at most 1 left. So we have a 1 forward. That's kind of what's going on, right? So we've done this one. We've done this one. What about SCET? Notice that A cannot reach D anymore. So we have to figure out some other way around there. So we go S to C to E to T. So it's just the fully bottom path. What is the max flow on the bottom path, the bottleneck, excuse me? 3? Yes. So we augment all of these by 3. So this is going to become 0. This becomes 5. This becomes 1. This becomes 4. This becomes 1. And this becomes 3. Okay? Let's do SCEDT, right? So we can still, what's the bottleneck of SCEDT? Yes, 1, 1, 1, 1, right? So this becomes 0, this becomes 4. S to C, this becomes 0, this becomes 5. CE, we go from this edge, this becomes 0, and this becomes 1. And then D, this becomes 1, and then backwards becomes 2. Excuse me, 1, yes. Notice though, this edge went from 1 to 0 to 1. In some sense, we originally planned to send flow down here, and then we kept the backwards edge so we can undo that. And then we found actually we can send one more if we do this other path. So undo that mistake. So we undid a previous decision we made, but the same number of trucks are going where they're supposed to be, right? So this edge basically flip-flopped a couple times. That's, to give you a hint, that's kind of why the runtime of the runtime of Ford-Fulkerson, were we to analyze it, would be very bad, actually. It's a function of the maximum weight rather than any specific dimension of the graph, which is not so good. Correct, so that's SCE dt. All right, we have one more, SB dt, right? S to B to D to T, I agree, that's 1. So 5 becomes 4, we have a backwards of 1. 1 becomes 0, we have a backwards of 1. And then D, this becomes 0, we have a backwards of 2. Okay? Now I want to highlight something. Why do we stop? It is disconnected, but notice, like, where is it disconnected? It's actually disconnected in a couple places. Notice that T has no incoming edges. Literally, if I were to draw this nicer, you would notice that T looks like this. Right? The incoming edges to T are all 0. So T has 2 outgoing edges of weight 5. Right? So nothing else can reach T at all. These 2 edges are gone. And in fact, that's not the only 2 edges that are gone. But that's just an example. So according to the way we've defined Ford-Fulkerson, we stop. Okay? This is the execution of the algorithm. We should not be convinced that it works, though. We should just be convinced like that found a flow. How do we know that it's maximal? We need to now certify that, and that's where the next part of the Ford-Fulkerson algorithm comes in, the max flow min-cut theorem. But are there any questions on that so far? Okay. So to prove 2 numbers are equal, it's sufficient to prove 2 things. First, we can argue every flow is less than or equal to any cut. Then some flow equals some cut. If we can prove those 2 things, that'll be enough for us to say that the max flow is equal to the min cut. Okay? Why is every flow less than every cut? Let F be any flow, and C1, C2 any cuts. We observe by the whole bottleneck property that this flow is less than C1 and F is less than C2, right? No matter how you position those cuts, the flow has to go through both of those. So it must be less than both of those. But then from there we know that F is less than the min of both of those, right? If a number is less than 10 and a number is also less than 7, then it's just less than 7, right? But since this is true for every flow and every cut, we know that every flow must be less than or equal to every cut, right? So this is sufficient. So this implies every flow is less than or equal to every cut. Choose any flow and choose any cut, the flow will be less than the cut. This is sufficient to demonstrate that. It's kind of a trick of the light, though. So any questions on that? Any not understanding that to be true? This follows again from the fact that the flow has to go on the cuts. The cut is the capacities, right? So whatever flow goes on there has to be less than or equal to that, no matter how you position the cuts, just by the constraint properties, right? Question?
So it's pretty much just the cut property.
Be careful with the cut property from
It's a little different, right?
Kruskal's. They are related, and I'm sure there's a very technical way to generalize both that kind of has a symmetry, but I would stay a little bit away from that. Just as you'll see in the linear programming lecture, it generalizes in a different kind of way. It's not wrong to think about that, because when you in the cut property, you're choosing perhaps singular edges off every cut, the least of which. But on a flow, you want to kind of like maximize the amount, so you can choose multiple of there. And there's no problem with your flow being, for example, cyclic cycles and repeated things and these kinds of things. It doesn't really. Thinking about the flow, a cut as a disconnection is important, and that's the relationship. That's the most important relationship between the two. Right. So now we just need to prove, do we agree first off that we've proven that the max flow is less than or equal to the min cut? Okay? Now we need to prove that the output, that we just need to find one flow that's equal to any cut. If we can find any flow that's equal to any cut, we're done. Okay? Here's how we can find a flow that's equal to any cut. It turns out Ford-Fulkerson solves two problems at the same time. That's kind of one of its elegance points. It doesn't just find the max flow. It simultaneously finds the minimum cut. And because it finds a minimum cut that's equal to the max flow, those two numbers are identical. After completing Ford-Fulkerson, run explore on residual graph from S. Here's the first thing to notice. T is unreachable. Why? Yeah, the stopping condition of Ford-Fulkerson is when there's no longer an ST path. So if the algorithm is finished, there is no longer an ST path. So calling explore from S will not reach T. Fine. So let L equal the set of vertices explored from S, and let R equal whatever's left. Right? Let's say V. That's going to be your cut. Let's call explore in this graph here. What vertices are reachable from S after we finish the computation? Yeah. Now, why is nothing else reachable from those? So I'm asking two questions. Let's consider D, okay? Why is D not reachable from A? As a max flow question and as a min cut question, why is this a minimal cut? First off, what is the cut value of this? What is the value of this cut?
7.
Yeah. And what was the value of our flow?
7.
So we have a flow that equals a cut. So, but why is this a minimal cut? Actually, we don't really need to argue about that, but the fact that we found any cut that equals any flow is sufficient for us to know that the max flow is equal to the min cut, right? But at a deeper level, why is this the cut, right? So for example, what I mean is, why is D not reachable from B or even A? There used to be an edge there, and now there's not. So what?
You've used up the capacity.
Yes. So the fact that you went from something like this, you went from some capacity to, let's say the cut goes like that. You went to having a forward edge of 0 and a backward edge of capacity, right? The cut stops exactly where the edge is fully saturated. If the edge is not fully saturated, then you can explore further. For example, S can reach A because that edge is not fully saturated. You still have one left. So S can touch A. Fine. A cannot touch D because that edge is fully saturated. In fact, it has capacity 2. The flow on that specific edge is of value 2, right? So the border, the demarcation line between the cut is exactly a set of edges that are fully saturated, right? So if a set of edges are fully saturated, the definition of a cut is the sum of the capacities. So the capacities are the flow. So the flow is equal to the sum of the capacities on the cut. That's why the max flow is equal to the min cut, right? I'll say it again. The edge of the cut is where the flow stops, right? If an A is not reachable to D, that means this edge has to have 0, right? So 0, 0, 0, right? You can't reach C, D, or E or anything from there. Why? Because all the outgoing edges from there have 0. Because they have 0, we know that C minus F is 0. So if C minus F equals 0, that implies that F is equal to C. So the flow that we sent on that edge is full. And because the cut is equal to the sum of the capacities, we know that's equal to the flow. So the maximum flow is equal to the minimum cut. Not just because we have a max flow, we have a cut equal to a flow, but in fact, simply because the edges are saturated do we get this, right? That's the reason why. So not only does the forward Fulkerson tell you how to find a maximum flow, it also, analogously, at the same time, tells you how to find a minimum cut. So the algorithm solves both problems simultaneously to find the same solution. And in fact, as it's maximizing flow, you can think of it as the fact that every time we found a path, we were increasing flow, right? We added one truck and then two trucks and then three trucks and then one truck and so on, right? But as we were doing so, we were also decreasing the minimum cut. As we were considering larger flows, we were decreasing cuts. We're considering smaller cuts. Eventually, they're optimal when S and T are disconnected, and those two values must be equal. This is the Maxwell min-cut theorem. These two values are the same. Are there any questions on the forward Fulkerson algorithm, on its correctness? Right? And this will be an important trick later. You don't need to prove optimality or equality of something as long as you find one thing that's equal of a maximal set to something that's equal of a minimal set. If those two are equal, then you know it has to be optimal. Right? Questions on Maxwell min-cut? Yes?
Why do you have to put the backwards paths?
So intuitively, my perspective is that you can think of forward Fulkerson like a greedy algorithm, but it keeps information there that allows it to greedily undo a previous greedy mistake. So by keeping a backwards edge, let's say what it does is it repeatedly finds paths, fully saturates them, and then just goes on doing that. If you did that on the original graph and not the residual graph, you would not find an optimal solution. The greedy algorithm is not optimal for this problem. And I could come up with a counterexample, but perhaps you believe me. So instead, by having a backwards edge, you allow yourself, while still finding forward paths, to undo a previously made decision. For example, this edge flipped flop a couple times, right? We decided we're going to send one down. But then when we found this path, that's not actually a path. What it's saying is, if I don't do that, and I did this thing instead, this is a better solution, right? So I like to think of it as the backwards edges allow you to, in a forward-thinking way, undo previous things, right? Another hint on kind of the beauty here is that if you have a capacity, if you have a cut that is saturated, notice there should be no trucks going backwards. It doesn't make sense. No flow solution should have a sequence of trucks stuck in a cycle or something like this, right? So notice that none of the edges that go backwards from the cut in the original flow graph have any value, right? In the residual graph, they do, but not in the original, when you actually look at what the flow is itself. More questions? Conceptual understanding here more important than algorithm, right? All right, let's take a break.